Without further ado, I would like to welcome everyone and introduce you to our tutorial, Graph Neural Networks in TensorFlow, a practical guide. The tutorial will be 1.5 hours, so we will start as we are starting 10 minutes later, and we will end 10 minutes later at 3:10 p.m. Eastern Time. We have the tutorial website QR code available to you, and it's also up there in the TensorFlow GNN GitHub. So now I will do the welcome part for Bryan, who couldn't unfortunately join today. Bryan is our lead of the TF-GNN team, and my name is Anton. I'm a research scientist in the Graph Neural Networks team at Google. This tutorial consists of 2 parts, 2 lectures, and it's paired with 2 Python notebooks, which cover 2 aspects of working with TF-GNN. One is kind of basic, how to run, how to do academic style medium-sized data, and the second one is more advanced modeling. First part is covered by Sami, and the second part is covered by Neslihan. And the notebook and slides can be found on the GitHub right now. Recordings will be uploaded to Log YouTube, but we will also add them to the tutorial website later on when they become available. So now I will do 5 minutes of welcome and general introduction. Then Sami will take over the first part, and then Neslihan will take over the second part of the tutorial. Graph Neural Networks team at Google's mission is to make it easy to use graph structure data inside neural networks and deliver value through them. To do that, we have kind of different work streams. We do research, publishing at premier conferences. We build and maintain a library to express these models. We also build infrastructure for training and deploying GNNs at tremendous scale. And we also write custom models for different applications. And you can see the illustrations of how, for instance, different components of TF-GNN work. They will be covered later on as well. One of the key challenges we encounter in daily work is that big graphs are very complex and they exhibit different properties to what we usually see in the academic data sets. So we have to have some more advanced modeling techniques, and some of which we publish. For instance, the Mixhop paper published in ICML 19 has access to multi-scale convolution and performs much better at less homophilous graphs than just plain GNNs. Another challenge we encounter many times is how to benchmark different models. So this year we introduced GraphWorld that allows you to benchmark a bunch of millions of models on millions of tiny synthetic data sets and kind of see the performance landscape changes in real time across various degrees of freedom. And the third big challenge that we encounter that we don't see that much in the research world is what to do if we don't have a graph, how to build a good graph. So Grail is our tool to extract graphs from data, and it's frequently like the first and major step in our graph mining pipelines. Graphs built from Grail are very homophilous, so they're kind of well suited for graph learning. We have a paper KDD and some paper dub that does kind of more advanced graph building and tells about how these things are actually used in production. So please give them a read. Graph Neural Networks team is as part of a graph mining research group at Google Research. We are frequently dealing with billions of nodes and trillions of edges. And to deal with data of this scale, graph mining team has expertise in algorithmics, advances, distributed systems, and machine learning. And the tools are powering a lot of Google products such as Search, Ads, YouTube Play, Cloud, and so on and so forth. And if you want to learn more about graph mining in general, we have Expo at ICML and a bit older but still good slides at NeurIPS 2020 that are available at these links. And if you don't write them down, we still have the slides available on the tutorial website, so be sure to check them out. Without further ado, I will introduce the presenters of the second and third part of the tutorial, Sami and Neslihan. Please take it away, Sami.
So now I'm going to talk about some background. We're going to do some recap of graph neural networks, and we're going to discuss some problems they solve. This section will be a good refresher for people who already know graph neural networks, but the people who do not deal with graph neural networks a lot, it will be a nice introduction. So I am Sami, and I'm also a research scientist at Google Research, and I work with TF-GNN. So what are graph neural networks? We're going to do some quick recap of graph neural networks. Then we're going to talk about some tasks that are solved by graph neural networks. So to explain graph neural networks, maybe we should make some analogy to some other kind of neural networks. So specifically, let's talk about in vision, the popular neural networks, there's a class of neural networks that are called convolutional neural networks, and they're very popular. So a convolutional neural network, because it's a computer vision neural network, it takes as input a picture, a photo, and it gives you an output depending on how you train it. So it can give you the class of the main object in the photo. So it can tell you that this is a dog, or maybe it can give you an entire sentence, maybe dog on a leash walking in snow, if you train it as such, or it could do some kind of segmentation. So for each pixel, maybe it can tell you what's the object belonging to each pixel. So in a similar vein, graph neural networks are also neural networks, but instead of the input being a picture, now the input is a graph. And the output, well, it depends on how you train it. So maybe the output could be node classification. So here, node ID 0, maybe you want to classify that they like basketball. Or maybe the output could be link prediction if you trained as such. So maybe it should tell you that nodes ID 0 and 1, maybe they should be connected. And another problem that GNNs are good at is graph classification. So perhaps if the left graph was a program that contains maybe it's like a computer program, and you can describe a computer program as a graph, you can have a GNN that can tell you, does this computer program contain a virus or doesn't contain a virus? So these are very popular problems: node classification, link prediction, and graph classification. We're going to talk a little bit about them right now. Before we go into the details of what these problems are, let's just very quickly summarize what is a graph. So a graph consists of nodes and edges. When you depict it on the whiteboard or on a paper, usually people draw a node as a circle and an edge as a straight line connecting these circles. Nodes indicate objects or entities, and edges represent their relationships. So you can, for example, think about a social network, an online social network. Here, each node could be a person or could be some kind of post or comment. And an edge could be between two people, a person and a person. They could have an edge if they are friends, and a person could also have an edge to a comment if they like the comment, for example. Additionally, you can have features. So each node could have some kind of feature vector. So for instance, a person, you could maybe for each person, you might know their age range, you might know their gender, you might know their location, and you might know the language that they speak. And for a comment, you might store the actual words in the comment, or you might store the language representation, which could be like a BERT embedding or a word to vec embedding. Now, if you have such a graph, what does it mean to do machine learning on this graph? We talked about the few tasks that people attempt. Let's start with node classification. So given the graph that we just demoed, maybe you're interested in mapping every node in this input graph to some kind of output. You want to map the nodes into the advertisement space, perhaps. So maybe you're interested in predicting the advertisement interests from each node on the left. So basically what people do, they say, okay, we want to project the same graph, which is the same nodes and edges from the left. And they say, okay, we have a graph on the right that instead here, you only show, let's say, the labels that you know about. So maybe this user right here on the top left likes advertisements about cars. The bottom right user likes advertisements about fashion, etc. And maybe you're interested in predicting the label for the center node here. So the graph neural network will take the input graph on the left, which it's nodes and they have features, and progressively map it into the output space. The output will also look like a graph, and each node now will basically, the graph neural network will be outputting the label. And in this case, if we train for advertisements, then hopefully it will be mapping each user into the advertisement that they like to click on. So the way graph neural networks do that, they are trainable transformations, and they are basically learning some weight matrices. They're learning some weights. So they would learn what is the weight vector, or the space of the weights that the center user should have, and what about the users that are immediate neighbors of it? What about the nodes that are 2 hops away? You can, if you stack this neural network layer by layer, then basically each node will learn how to produce its labels given the neighborhood surrounding it. For usually each graph neural network layer, each node will look only at its immediate neighbors, but there are some models like mix-hop where each node can look at its immediate neighbors and further away at every graph convolution step. In addition to node classification, GNNs can also do link prediction. Here you have a graph and you're interested in predicting if there should be a link between 2 nodes. And for example, this could be used for friend suggestion if you have a social network. Lastly, in the problems that we talk about, GNNs can do graph classification. Here, the problem is to process an entire graph and to emit a label for the entire graph. So for instance, if your entire graph was denoting a chemical molecule, maybe you're interested in running this molecule through a model, some message passing neural network, and then you want to predict some graph level information, such as how much energy do you need to break up this molecule into individual atoms. Now, since graphs are general data structures, you can map many data domains onto a graph. Since you can do that, then with these GNNs, since the GNNs can solve general problems of link prediction, node classification, then as soon as you convert your data into a graph structure, then you can immediately run a GNN on it and solve those kinds of tasks. So now we're going to talk about some different applications and how you can map them onto a graph, and then basically what is the utility of doing these link prediction and node classification. So we're going to go through a few applications. And the first application is a social network. We just talked about it. Your nodes here could be a user or a comment, and the edge could be a friendship or a like. And if you do node classification, then you are predicting perhaps the advertisement preferences for the users. And if you're doing link prediction, you could be predicting friend suggestion, which people should be friends, or you could be predicting some things that should show on the home feed. Which comments should I show to the users? And if your graph was a drug-drug interaction graph, here each node could be a drug, and each edge could mean an interaction, which means you shouldn't co-administer them. So for example, people shouldn't take alcohol and ibuprofen at the same time because they could cause a kidney failure. Knowing a lot of these edges now, like having this kind of graph, you can now do node classification. And if you do node classification, you might be interested in predicting the biochemical or biophysical properties of each drug. For example, if it's toxic or not, its boiling temperature, etc. And if you're doing link prediction, you're trying to predict these interactions. Which drug should we not co-administer together? Of course, when you have a graph neural network to predict something like this, like some sensitive, some like chemical attributes, usually it's better to test them in the lab before you commit to these like interactions, let's say. And if your graph perhaps was a user video watch graph, then your nodes could be a user or a video. And here it looks like a bipartite graph. Each edge could be if the person liked the video or if the person watched the video. And if you do node classification, perhaps you're interested in predicting the category of the video. If is the video about cat or mathematics, depends on which users interact with it. And if you do link prediction, you might be interested in video recommendation. And another popular kind of graph is a citation network. Here, each node is an article, an academic article, and each edge is a citation. So if there's an edge from a paper to a paper, that means one paper cites the other. And if you do node classification, then you'd be interested in predicting the article category. Is this paper about arts? Is it about science? Is it about sports? Just given basically the features of the paper and who cites the paper and which papers this paper cites. And if you do link prediction, maybe you're interested to predict related work. Are these two papers related? And of course, there are many, many more applications that we can enumerate in such a short presentation. Graph neural networks can find shortest paths. They can measure graph distances. They can do subset selection. They can also solve integer linear programs. They can solve combinatorial problems, modeling physics, physical dynamical systems, and there are many, many more things you could do with graph neural networks. So now we're going to do some high-level overview of TF-GNN. We're going to show some practical considerations when someone wants to train a GNN on their data. What are some things they think about, and how does TF-GNN provide solutions for these things? The usual general setup is someone wants to do some training. They have some kind of graph data, and they want to train a model on this graph data. So they train the model somehow. And when you do this, what are the things that you think about? So of course, your graph data has nodes, edges, and features, as we discussed. And there could be labels either at the node level, at the graph level, or at the edge level. And there are, of course, many GNN model architectures out there. So perhaps maybe you're interested in training some GCN with distance encoding to do link prediction, perhaps. So let's think about some considerations that people could be thinking about. The first consideration is the data store. So is your data set, your graph, is it stored on a relational database? Maybe it's stored on a CSV file in some SQL or on some spanner relational database. Or maybe your graph is serialized, so it may be stored as TensorFlow examples on disk. If you have any of those, then we have a unigraph data reader that allows you to read serialized or relational databases. Perhaps your graph that you're interested in is an OGB or some academic graph, like OGB graph, network X graph, etc. We also have a lot of readers for these academic graph datasets. Another consideration is the GNN model. So maybe, of course, which GNN model you should use, well, it depends on your data. So maybe your graph, maybe the nodes are images, or maybe the nodes are video, maybe the nodes are textual, they're text. Because TensorFlow GNN is a native TensorFlow citizen, then you can use any TensorFlow model. So you can use any pre-trained or untrained model for images, for video, for text to process the node features. And depends on your task. So maybe you have a consideration like maybe you want to do node classification or edge classification or graph classification. TF-GNN implements a lot of objectives for node, graph, edge, semi-supervised learning, unsupervised learning, or supervised learning. So you can immediately just use these pieces that we implement, just plug them all together, and you can train a system basically with very little effort on your data set. Maybe you know something special about your data. You have some kind of inductive bias on your data. So you can use any layers. Like, for example, you can use Euclidean equivariance layers. You can use residual connections if you know that your data maybe is invariant to Euclidean rotations or translations. The last consideration that you could be thinking about is your training pipeline. How should you train? So if you're training it standard, if you have a data set, you want to put this data through our model, and then you want to minimize or optimize some objective, then we have this runner, we call the TF-GNN runner. It's low code. You don't have to write much code. And it's a good fit for many of the production use cases. But maybe you have a custom training pipeline. Maybe you want to adjust the gradient somehow. Maybe your graph is not given. Maybe it's latent. Maybe you want to do some transfer learning. For these custom pipelines, we show some examples how you can roll up your training pipeline from scratch. And each pipeline is 20 to 50 lines of code. You can copy paste it and adjust it the way you see fit. And another consideration is on the graph size. So your graphs could be small. In that case, you can do full graph training, as in observe the entire graph at each training epoch. Or maybe your graph is medium size, maybe it's less than 100 million nodes and edges. You could perhaps be doing on-the-fly sampling, so taking subgraphs uniformly at random, have the graph in memory and do that on the fly sampling. Maybe your graph is very large. It has more than 1 billion nodes and edges. We have a distributed sampler that you can be running, and then you can feed the output of the sampler to our runner. So you have all these options. Now it's time to do some hands-on, just to talk about TF-GNN, how you can run TF-GNN on a single machine. And then afterwards, I'll pass it to Neslihan, which she will talk about maybe if you want to build more complicated models. So now let's do this maybe like end-to-end pipeline. So this tutorial is linked from the website of the tutorial. There's a log tutorial, and within it we have a few Colab tutorials. So this is called Code Tutorial 1. You'll find it there. So let's go through the tutorial. So this tutorial is to do node classification using TF-GNN. It gives you some hands-on experience to do that. The first thing that the tutorial asks you to do is to install TF-GNN. I will not do that because I already have it installed, but you should run the install. Then the second thing to do is to do the standard import. So you'd import TensorFlow and you'd import TF-GNN. I just ran this all. And the last thing you have to do in terms of imports is just import the things that we'll be using. We'll be importing the data sets. This will allow me to just basically say, oh, use this OGB data set or use this Platinoid data set, etc. There's a model file that implements a few useful models like GAT, GCN, etc. We have a lot of layers being implemented, transformers and many GNN models that you might like. We also bundle a few of them in this models file. And we have other utilities. Maybe I'm not going to walk through them in detail. Reader utils, it allows us to read some things from the output. Like we put the graph through a model, then we read the nodes that have labels, let's say, to be able to measure the objective function. And we have some helper function that helps us to do sampling. I'm going to run this right now. Here we have some settings. This is like when we're training in this tutorial, we have to specify three main things. The first thing is the data set. The second thing is the model. And the third thing is the training loop. All these are customizable using this user interface. So you can say, how do you want to train? You want to train full graph, as in no sampling, or you want to do on-the-fly in-memory sampling? Let's train with on-the-fly in-memory sampling. Here we've listed down a few of the data sets that we support. We support many, many more, but then on this code right here, we just listed some of them. So let's say we want to train OGB in archive. And since we're doing sampling, it will ask us basically, what's your batch size? So when you're training from a full graph, you don't have to specify this because the entire graph will be observed at each training step. But since we're going to do in-memory sampling, we're telling this script to use 100 nodes each time from the training set. And for each of the 100 nodes, we're going to take a subgraph around it. We're going to feed all these subgraphs. So we're going to take 100 nodes at a time, 100 subgraphs at a time. Here, it's asking us if it should use the validation set as part of the training set. The OGB setups, they allow people to use the validation as part of the training, but only after the hyperparameters have been finalized. So let's maybe think that this is our final model. We have a couple of architectures, GCN, some other simple model, JK network, GAT-v2, residual GCN. All these models are implemented in the models PY file, which is imported above. Each of the models can accept some parameters, like the depth of the neural network, if you should have dropout or not. So each of those models, as it's implemented in models PY, you can look at it, you can see what are the arguments it could receive, and you can override any of them in this dictionary. And since GCN model likes the graph to be undirected, we're gonna tell the script to undirect the graph. So to make it undirected, as in each copy that shows in one direction will also be copied to show up in the other direction. This prompt here, embed featureless node dimension. The OGBN archive, every node has a feature vector, which is the word-to-vec embedding. But for other data sets, for example, OGB and MAG, some nodes don't have features. So if some node doesn't have features, it will be embedded in 32 dimensions. You can embed it in a different number, different size of the embedding table. And finally, we are telling it to train 50 epochs and to evaluate after every epoch with this learning rate. Of course, we can modify any of this. I just wanted to walk everybody through them. Now there are a few blocks. The first block is to prepare the data set. I am not gonna show you this code line by line. Maybe I'll just show you this prompt. So as you run this data set, actually, maybe I should also run the one above because I have it. So I just ran the one above. Let me run the data set again. So after this code block executes, we get these objects, train DS object, validate DS, and test DS. These are TensorFlow dataset objects, and you can basically just pass them to your model. You can make a model and say model.fit, and you can pass it this trained dataset. You can say model.evaluate, and you can pass it the validation or the test DS. I will not go through this code of the setting up the dataset because I think it's more interesting to go through the code of the model and the entire training loop, but we can come back to it if we had time. Now this is the code of setting up the model. Let me run this. We're calling a function on the models.py we imported. This function says make model by name. We give it the name of the model. In this case, we set it to be GCN. And we give it the number of classes. OGBN archive has 40 classes. This number classes variable was initialized for us in the above code block when we're loading the data set. We also give it some L2 regularization, and we give it the model arguments, which in this case, some dropout and specifying that we only want 2 layers. And here we're setting up the GNN model. Maybe I'll actually go bottom to top, perhaps. So the output of this block is to make a Keras model. And when you make a Keras model, basically you say tf.keras.model, and you give it the input and the output. From this input to this output, there is a computational graph. It's the TensorFlow graph that can transform the input graph into the outputs. So let's look at how the transformation happened from the input to the output. So if we scroll a little bit above in the code, we see that this input graph is initialized to something called input. And this input is basically a placeholder. It doesn't have the node features or the edges. It's just a placeholder. We're going to map this placeholder through the model. So the first thing we do is we make a copy of it, just a reference to it. And we have a couple of functions that will map graph to be a function of the graph. And again, we do the graph to be a function of the graph. We're going to show these functions in less than a minute. So the first function is basically saying, I would like to map the features of this graph through this function, init node features. So this function right here is defined above. By the way, this graph, we have something called, it's basically, we call it the graph tensor, and Neslihan will describe it more. But for now, let's just think that there is some representation of a graph that has nodes and edges, and you want to map this representation through some number of transformations, and you want to optimize these transformations. And we're going to talk soon. Neslihan is going to tell us what does this graph tensor look like. But think about it now, it's a representation of your nodes, edges, and their features. So we first pass them through this initialization function. And after the initialization function, we call the model function. In this case, our model was a GCN model. So let's just like pause here and look a little bit upstairs on what is a set initial nodes features function. The set initial nodes function will basically initialize the node features, as in when you call it, basically it will say, okay, what is this node set that I'm initializing? We will talk about node sets soon when Neslihan is giving her presentation. But basically think about this as something that can just read the correct feature vector that you want the GNN to work on top of. Your correct feature vector might come exactly from the graph, or maybe your graph has pictures as nodes, and maybe in this initialization, you want to run a vision model over these nodes, and maybe you want to pass the output of the vision model to the graph neural network. And of course, this function itself could be it is trainable. So if you have any trainable matrices in it, they'll be trained by default for you. But this function, you can think about it for now as something that can set up the input to the GNN. So it's extracting from each node the features that the GNN should read. So here now this graph has the features of the GNN at every node, and then we run the actual GNN over here. And finally, we want to be reading out the activations for the nodes that are labeled. So this read out seed node features takes the graph with all the latent vectors at this point, and it will basically say, read me the node set that's labeled. So in this case, OGB and archive only has a single node set, which is the papers. So it will basically give you the activations for the nodes that have labels. The last part is the optimization. So here, actually, this is not being used. So sorry. The optimization here, this is standard. If you've done TensorFlow, you make an optimizer. Maybe you want to use Adam or stochastic gradient descent. And then you define your objective function. Here we want to do categorical cross entropy. We're basically telling it that our model is outputting logits. So it will take the softmax for us. And we're telling it that please compute the sum over the batch size. Of course, sum and mean make no difference, especially when you use some kind of Adam or some kind of optimizer that divides by the volume, I want to say, or the variance of the gradients. Then you want to compile the QRS model. After it's compiled, the graph inside of the QRS model will get optimized, so it becomes faster to do the learning. And the last thing is the fit line. So let me run this and let me run this one. So now here we're gonna see it basically training. So now it's training over the first epoch, and you can see now the validation accuracy climbing to this number. You can basically wait for it, modify the model a little bit, maybe choose a different model, etc. So this tutorial hopefully gave you a very quick overview of the different pieces of how you can use TF-GNN. There's one more part that I will highlight before I pass it to Neslihan. There's of course this one cell here that you can run to test the performance on the test data set. I'll skip it because the model is still training. The last file I want to show is if you have a data set that's not implemented in TensorFlow GNN, how could you implement it? So you can go, we have this TensorFlow GNN. This is still an experimental, but hopefully this specific file will be moved out of experimental within the next couple of weeks. There's a datasets file, and to implement a new dataset, all you have to do is to implement this class. We call it mMemory graph data, and you have to implement these functions. You have to say, what are my edges? What are my nodes? And you also say, what are my features? What are my node counts? You implement these 4 functions. That's if you have node features, edges, and nodes. And if you have graph features, you also implement a function called context. And once you implement all of those, then you can immediately inherit a lot of the good stuff that I showed you. You can do sampling on the graph, you can do training, you can plug it into any TF-GNN model, etc. And I'll pass it to Neslihan right now.
So welcome to the second part of the workshop. My name is Neslihan Bulut. I'm a software engineer in Google Research working for the Graph Neural Networks team. So in this part of the workshop, you will learn how to build graph neural networks in TensorFlow and TF-GNN. So here's an overview of the talk. Firstly, I will go over the main graph structures in TF-GNN. Then you will take a deeper look into the graph tensor internals, followed by the message passing primitive operators that you can use. Also, how to apply custom graph transformations. And finally, we will have a hands-on session building a graph neural network model with TF-GNN using a Google Colab notebook. So TF-GNN library comes with native support for heterogeneous graphs where you can have multiple entities and multiple relation types. Edge level models where you can update the edge states, inbuilt GraphNet, as well as MPNN architecture supports. Tasks you can define at graph, edge, or node levels. And you can also use hypergraphs, which is basically a generalization of graphs, which can connect multiple vertices instead of just two vertices. So graph neural network models train over graph data. And in TF-GNN library, graph data is declared using a graph schema and represented as graph tensors. So the graph schema is a protocol message to declare each node set, ad set, as well as their respective features and the context, which is a graph level feature and applies to the whole graph. Note that since TF-GNN supports heterogeneous graphs, each different entity or relation can be represented as a separate node set or ad set. For example, in an academic paper citation network, each entity such as the author, paper, or venue can have their respective node sets. Similarly, different ad sets such as rights or sites will have a separate declaration. You will define the graph schema once to build your graph neural network model. And graph tensor is a tensor format to store the actual data. It's a composite tensor which holds the node sets, ad sets, and the context feature, along with the entity relations declared in the graph schema. And we can store both dense tensors as well as variable size features with the TF-ragged tensors in the graph tensor format. Now let's take a look at a concrete example how the graph schema and the graph tensor work together. Let's first add this node set named user, and graph tensor can have multiple nodes of this type. Here in the graph schema, we declare the user node to have these features, name, age, and country, and respectively we'll have the feature tensors in the graph tensor with the accompanying features for this user node set. Here we can see that there is this is-friend relation between the user node sets, and the respective directed edges can be seen in the graph tensor. And we can have different node sets, such as the item node set here, with price and category features, and graph tensor can have nodes of type item with the respective features. And a general guidance for these heterogeneous graphs is to represent entities with the same data under the same node set. For a purchase ad set between item and user nodes in the graph schema, graph tensor can have actual edges among the respective node sets. And note that the ad sets are directed. And to represent an undirected graph, you can either add edges for the opposite direction as well into the same ad set, or declare another ad set with the reverse order of connections. Finally, you can declare a context feature such as the scores here, which is a graph level feature, and it will respectively be present in the graph tensor. And the context is a graph level feature applying to the whole graph. And you can use this for graph regression or graph classification tasks. An example can be given from the chemistry molecule graphs, where you can use the context to represent, let's say, toxicity of the molecule. Now let's look at the graph tensor in more detail. We mentioned it's a composite tensor, which is similar to how TF-ragged tensors and TF sparse tensors are generated, are built or declared. And this is to help with working with TF data, as well as using it as input and output from the Keras layers. And you will find three main pieces in the graph tensor, namely the node sets, ad set, and the context. And each of these is called a graph piece with fields to describe the feature information as well as the respective structural information. Now let's look at the depiction of a graph tensor. So each node set graph piece has a dictionary of features keyed by the feature name, which is a string. And these features can be fixed dimensional or variable dimension. We can have variable dimensions, and we use dense tensors and ragged tensors respectively to represent each. And different node types will be a separate entry in the node set graph piece dictionary keyed by the node set name. So here you can see the item node set with prices and category features. Category feature has a fixed dimension across the nodes in the item node set and represented as a dense tensor, while the prices feature has a variable length and represented as a TF-ragged tensor. each of these feature tensors will have their first dimension as a number of nodes in the respective node set. So basically this way we can access each node from this features tensor for their respective feature encodings. And the AdStats graph piece is also a dictionary keyed by the AdStat name. But different from the NodeSats representations, AdStats has this adjacency structure that stores the edge endpoints using the source and the target tensors. So each of these tensors keep the node IDs for the source and target nodes, and node IDs can be used as an index into the NodeSats feature tensors. The is-friend relation here is a relation among the user's NodeSat. So the adjacency source and target tensors are going to be indexes into the user's NodeSat. For example, let's look at the first entry in the source tensor, which shows value 1. So this points to index 1 in the user's NodeSat, which is the user with name York, while the respective entry in the target tensor is 0, which points to the index 0 from the user's NodeSat to the user with name Shaun. So different AdStats will also be added as a separate entry into the AdStats dictionary. AdStats can also have features similar to NodeSats. And here the purchase AdStat has this feature named time. And the time feature of this AdStat's first dimension is going to be the number of edges in the AdStat to be able to identify, the respective feature for a given AdStat or for a given edge. And the number of edges is 4. You can see the first dimension of this time feature is also 4. So in addition to AdStats and NodeSats, there's also the context features, which is used to represent graph level information. Here you can see the scores feature, which can be used for a graph level regression task. And you can see the scores feature also, represented at the graph level. There are multiple ways to create graph tensors. You can create them manually using the graph tensor.fromPieces API. Normally, you don't have to do this manually. And there is also a standard graph datasets library package you can import from the TF-GNN library, which is under this TF-GNN examples in-memory datasets package. And you can access the graph tensor representations of these datasets. So Sami mentioned this in-memory sampler. We can also use the in-memory sampler to subsample graph tensors on the fly. And you can also get a handle to a graph dataset using the in-memory tool. And we also have a distributed sampler, which is a TF-GNN sampler to create graph tensors from serialized TF example protos. And the way to do this is through this TF-GNN parse single example API. And for large-scale datasets, this is the sampler neighborhood, as well as like some importance-based sampling you can do with the batch sampler. So with a reference to a graph tensor, now you can access the NodeSats features by, as shown here, by firstly using the NodeSat name as a key into the NodeSats dictionary, and then using the actual feature name to access the feature tensor. AdStat features can also be retrieved with a similar access pattern, firstly keying into the AdStat's graph piece with the AdStat name, and then using the actual feature name. And graph tensors are immutable structures like other TF tensor objects. So if you want to replace any of these features or add any brand new feature, you can use this replace features API. In this example, we are replacing only the NodeSats graph piece features, while the unspecified context and AdStat tensors stay unchanged. And different from the context and NodeSats, within the AdStats, there is also this adjacency information, which keeps the directed edges, not endpoints. So the adjacency structure keeps this directed edge information using a source and a target tensor. And these are both integer tensors that keep an index ID to the respective node set. So in this code snippet, you can see how to access node features from using the adjacency source tensor, which keeps an index into the node set's feature tensors. So firstly, we get the source IDs, the node indices from the adjacency source tensor, and then having a handle to these hidden state tensors of the node set, we can use the TF-GATHER to access the respective features for each node in our source tensor. Now let's take a look at how message passing happens over the graph. There is two main low-level operators that support sending data across the graph. These complementary operators are the broadcast and the pooling operators. So here's an example of a broadcast operation using TF-GNN broadcast not the edges call, which sends this edge feature from the source node to their adjacent edges of the edge set is friend. And this function takes a graph tensor and returns a TF tensor. Now let's recall our graph. So the isFriend edge set had these two edges, and we want to send the edge feature from the source nodes to their adjacent edges. So the users with name Jorg and Yumiko here is the source nodes for these two edges in the isFriend relation. So the return tensor from this broadcast operation is going to have a value for each edge in the edge set. So the first dimension is going to be 2, which will be the number of edges in the edge set. And you can think of the output from the broadcast operations as another edge set feature. And there's additional broadcast operators in TF-GNN, such as broadcast context to nodes and broadcast context to edges. These functions will broadcast messages from the context to nodes and edges respectively. So now that we have these broadcasted messages, so how can we aggregate this information? We can use this pool edges to node operator for that, which will aggregate the broadcasted messages from the edges to the nodes with the node tag here, TF-GNN.target, which is the target endpoint of the edge. And you can also set this node tag to TF-GNN source, which will be the source endpoint. And here we are using some pooling to aggregate the broadcasted messages at the target endpoint of the isFriend relation. And this operator also takes a graph tensor and returns a tensor. And recall that in the graph, we had 3 nodes for the user node set. So the return tensor from our pooling operator will have an entry for each of the users in the node set. So since the first node in the user's node set is the target of both the edges in the isFriend relation, it's going to receive the value 59, which is basically the sum aggregation of the values 32 and 27, while the two other nodes in the user's node set don't have an incident edge where they are the target endpoint. So they are going to just receive a 0. And there is, all the other different aggregation operators, and you are also welcome to declare your own aggregation operator and use it with TF-GNN. There's also pooling operators available from nodes and edges into the context, into the graph context. And these are namely TF-GNN pool nodes to context and TF-GNN pool edges to context operators. So here's a typical flow of stages while building a graph neural network model. You can start with generating subgraph samples using either the in-memory sampler or our distributed batch sampler. Then you can transform graph features using the preprocessing step, and also generating the hidden state vectors, followed by several runs of graph updates with a graph neural network model, a readout layer which will extract relevant features from your graph to feed into the loss function to optimize the model weights. So during a feature pre-processing step, you can transform your features before feeding the graph into your model. So TF-GNN library has this map features keras layer that accepts callback functions to transform each individual graph piece, not sad, add sad, and context. And these callback functions can use keras functional API and depend on the input parameters to learn trainable weights. And here you can see an example for a callback to initialize the node sets. And it applies a linear transform. The callback applies a linear transformation for one of the features, and for the other categorical feature, it's learning and embedding. Then concatenates them and returns the tensor back. Return value from the callback functions can be just a tensor or a dictionary of tensors. And when the callback function returns just a tensor value, it will be mapped to the feature named hidden state. And this is the default feature named TF-GNN keras layers read from and write to. Now let's build the graph neural network using a using the keras sequential API. So we will be applying GNN layers here that transforms the graph tensors. A GNN layer receives a graph tensor as input and returns a transformed graph tensor as output. And in the keras sequential API, each layer receives its input from the output of the preceding layer. So this came up also a bit from during Sami's presentation, and TF-GNN library has this model subdirectory, which has implementation of various standard graph neural network architectures. In this example, we are going to use GCN and GATV2 model layers. So our first layer is the GCN convolution that will apply the GCN layer or the hidden states of the input graph and pass the output to the next layer. And here, after the GCN layer, we have the GATV2 layer, which applies graph attention convolutions over the hidden states of the input graph, which is the output of the previous GCN layer. You can add as many GNN layers as you want to declare your model based on your performance metrics. Now that the training completes, we will need to pick relevant features from the graph, which is the readout layer to make our prediction hat. And here I will show you a couple of different examples that you can make it more sophisticated based on the problem at your hand, problem you are trying to solve. So if your task is to classify each node in the graph, then you can use this TF-GNN keras layers that readout, initializing it with the node set name, and this will return states, which is the hidden state, the default value of each node for the specified node set name. If, on the other hand, if you have a graph level prediction task, you can apply pooling to aggregate the node states from the graph at the context level. And in case you have a subsampled graph, then you can have a task to classify the root node, which is typically the central node for a subsampled graph, and calling TF-GNN keras layers readout first node will return node states for the root nodes of the graph. And after each of these layers, you can apply a linear transformation to get the logits layer for your model. Here you can see examples that is used for a binary classification problem. So we just use the dense layer with one output for our binary classification task. So in this code snippet, keras functional API is used to build a graph neural network model. Input is a graph tensor, and we pre-process and initialize its features, then apply the GNN update to the graph, have a readout layer which extracts the relevant features from the graph to get our logits layer. We build and compile our model, declaring the optimizer and the loss functions, and use keras's model.feed to start the training loop. So we have completed the slides section, and we will proceed to the Google Colab notebook. And you can use your mobile devices to access the Colabs. We do have two, and using the QR codes here, we have two tutorials. In the student version of the Colab, there will be a task for you, and we will be going over the teacher version of the Colab together first. So in this Colab, we are going to build a graph neural network for a molecule property prediction problem. And for this problem, we are using this MUTAC dataset, which has 188 graphs in it. And each graph is a molecule, and node sets is the atoms. And we have an edge set, which is the bonds among the atoms. Both atoms and bonds has a feature that represents their type. And for the types, atoms has a one-hot encoding, that can have 7 different values, while the bonds have also a bond type, and that's also one-hot encoding, and it can be represented it can be represented by four different values. And we also have a graph level context that represents the mutagenicity effect of this molecule on a specific gram-negative bacterium, which is basically just a binary class that can take a value of 0 or 1. And as before, the first thing we do is installing the pip package for TensorFlow GNN library. Here you can see all the different Python libraries that we will use throughout this Colab that are being imported. And now we download the MUTAC dataset with wget call, which is going to give us the train and validation splits. Both of these data is coming in TF record file format. And in the files, we have serialized TF examples, which represents a graph for a molecule. And we get the paths for train and validation that we will use later. Here you can see the entity relation diagram. So we have this is a homogeneous graph where we have only one node type and one edge type. Nodes are atoms, edges are bonds, and we are going to use the hidden state feature name to represent the atom type and the bond type. And we also have the context, which represents the graph level label. And for the label, we are going to use the label feature name. So now let's see how we are going to build our graph schema proto from this entity relation diagram. So the protocol buffer format is this. You can access from the GitHub repo graph schema.proto in this path. And there is the context message. There is a context message with the label features. Let me try to zoom in a bit more in case it's not very visible. Okay. So the context has this label feature, which is a scalar feature that represents the mutagenicity of the molecule. And in node sets, we have just one node set, which is the atoms, and you can see, the feature declarations. And we wanted to represent the atom type as a hidden state because our TF-GNN Keras layers by default work on the hidden state feature, and that's the one we want to transform and use for our GNN model. So we use hidden state feature name. And we mentioned that this is a one-hot encoding that can take 7 different values. So the tensor is a fixed dimensional tensor with size 7. And bonds is our edge set, which is basically for this homogeneous graph between the atom node sets. And it also has the hidden state feature name used for representing the bond type. This was also another one-hot encoding that is taking 4 different values. So the dimension is 4 for a one-hot encoding to represent that. And now that we have the graph schema protocol buffer, we can use create graph spec from schema PB, which is basically the API to generate the graph tensor spec. So we are going to use this graph tensor spec to declare the input layer for our Keras functional model using the Keras functional API. How we need to use this, we will look into that later, and also to convert serialized TF examples into a graph tensor, we need to know the graph tensor spec. So we are going to use this function below. Let me show you. So we just mentioned that downloaded train and validation splits are using the TF-record file format, and you can use the TF-record dataset, passing it the file paths to read the data from disk, and you can use this map method to map each example, which is a TF example, serialized TF example format, to now generate our data set, which is going to be a graph tensor. And let's see how the decode function does this. So you first call this parse single example API, passing it to graph tensor spec, which we just acquired from using the schema. Record bytes are serialized TF examples, and this is going to give us the graph tensor. And we also mentioned that in the graph there is a label feature, right? We would like to extract that before feeding it to our model. So we just access the features dictionary of the context graph piece and pop out the label feature, and instead we will feed it separately along with our graph tensor into our graph neural network. So now that we have generated the graph tensor, let's take a look at one example there. So let's look at the trained data set by taking one element and using the get single element to get the actual data instead of the iterator. So it will return us the graph and the label. So let's look at the node sets atoms graph piece. This is the graph piece. This is the name of the node set that we declared. We can see, how this data is represented. We have a features dictionary, which basically is, as we mentioned before, is keyed by the feature name and the tensor representations of that feature. But we also have this sizes tensor, which is used to keep the number of nodes in the respective node set. So we can tell from here that there is 14 nodes in this atoms nodes in this graph tensor for the atoms. And so let's take a look at the features. So we had the hidden state feature for atoms. When we access that, we can see the tensor representation. You can see these are all one-hot encodings. And the shape here is interesting. So we had a 14,7. The first dimension is the number of nodes in the molecule in this graph, and 7 is the dimension of the actual feature. So bonds relation is actually an undirected relation. In order to represent this with the graph tensor, what we did is we added the edge pairs in both directions into the bonds at set. And let's look at the adjacency structure that keeps the endpoints. So you first access the ad sets with the ad set name and the adjacency structure under that, and use the source. So here we are looking at the source field, which is the source tensor. So source tensor consists of indices, which are basically indexing our atoms node set. And we also have a shape here, which is basically, as you learn throughout the presentation, the first dimension is the number of edges in this edge set. So there is 28 edges, and you can find the respective target endpoints for each of these sources in the adjacency.target tensor. So we also had the hidden state feature for the bonds, and so you can also similarly access that after indexing into the ad sets, then the features with the feature name. So these are also one-hot encodings, and the shape is the first dimension being the number of edges. So each edge has their respective encoding here. It's a one-hot encoding of fixed dimension for. And you can also represent variable dimensioned features, and that will be shown as a ragged tensor, and we will have some examples for that going forward. And context is this graph level feature. So when we look at the context graph piece, we see a similar structure, and there will be only one context per graph. So sizes shows just value 1. And label is a binary label, which can take either a value of 0 or 1. As you can see here, the value for this graph input for this label is 0. The label for this example is 0. So now let's continue with the actual training. Before we start training, we need to batch our data. And we have created our train dataset and validation dataset using the TF-Data dataset API. And we have these batch methods, and you can just pass the batch size, and you can call repeat to actually train over this batch size with as many epochs as you would like. And we also have this validation dataset that will be used below for training loop. And so here we have a function which will be returning a Keras model using the Keras functional API. And let's see, how it's going to build the model end to end. For the Keras functional API, the first layer has to be this input layer. And in order to declare your input layer, you need to have a tensor spec, and we declared our graph tensor spec that will be used to generate this first input layer. And as soon as you get your input graph, you will need to convert that into a scalar graph, because TF-GNN layers work with scalar graphs. And what this function does is it will be just merging all the individual graphs to generate a scalar graph in the scalar graph. And we will have an addendum section with more advanced topics that will talk in more detail about how the merge batch to components works under the hood. Oops. Okay. So let's continue with the pre-processing layers. Now that we have our scalar graph, we can initialize our node sets and edge sets before applying transformations. So we use the map features Keras layer with the callbacks to update the node sets and the edge sets. And for both of these functions are just applying a linear transformation over the hidden states of the respective graph piece data. But we also would like to add a new feature to our context graph piece. So basically, this context doesn't have any features, and we would like to add a brand new feature. And what we want to represent there is we would like to keep track of number of atoms and number of bonds in the molecule as a hidden state. So we can access number of atoms using the node sets sizes tensor, and similarly number of bonds, again the sizes tensor of the bonds at set. And replace features, we'll just replace the feature of the specified graph piece, while the rest of the graph piece data will stay intact. And the reason, as I mentioned, is because graph tensor is an immutable structure, so that's why we need to call this to update the graph and get a handle to the output as our new graph. So this is a helper function which just uses the Keras sequential API to create a small neural network for the upcoming layer updates that can be used for transforming the tensors. And in this loop, we are running graph transformations, update over our graph, and we are using by default here the graph update Keras layer. So TF-GNN's graph update Keras layer here is used to update the node states. So for that, it receives a dictionary of node set updates. Here we have a homogeneous graph, so we have just one node set atoms, and we use the node set update Keras layer again from the library. And this function or this layer is initialized with two inputs. First is a dictionary of edge set updates, edge set convolutions, and the second one is a next state function. So let's look at them in detail. So the first input is, as we mentioned, is a dictionary of edge state convolutions. And we have the simple conv layer from the library, which basically just does a simple convolution by concatenating the source and target endpoints of the edge set before applying a user-provided transformation function. But we also provide here a sender edge feature. And when we do this, what happens is it's also concatenating the sender edge feature, which is specified to be the hidden state of the edge set, to be concatenated with the source and target states. Then we apply this message function, which is our dance function we looked at above, and we do a sum pooling at the target endpoint. So here you can set the receiver tag to be also the source target, and that will be how the messages will be, where the messages will be pulled at. And you can declare your own convolutions to also update the or generate the messages from your ad sets. And for a heterogeneous ad set, you can also specify, a dictionary, in this dictionary, other ad sets, and you can even do apply parameter sharing in case the sizes of these ad states are compatible. Now you can use the same convolution for different ad sets as well. And we mentioned this next state function, right, which is the second input to the node set update. So we have some library functions for that as well, which is here the next state from concat function. This layer, the next state from concat layer, is receiving 3 inputs from the node set update call. The first one is the alt state of the node set, which is our atoms node set. The second one is a dictionary of message convolution outputs from the ad sets. And the third one is an optional context state. So when this function is called, it's going to just concatenate them and apply this user provided projection to return the result back. And all these functions that we looked at here has an extensive documentation in their doc strings, along with additional examples that you can check out. Also here we have used the graph update function to only update the node states at each iteration, right, at each graph update. But you can also use this to update ad states as well as the context state. And in fact, actually, the question in the student version of the Colab is going to be how can you modify this function to now update the context state, so you learn an encoding for that, and how it's going to change the downstream, the actual model performance. And as an example, we have also added these GCNN graph stage layers from the model subdirectory. And as you can see, these are coming with a bunch of different hyperparameters. And the suggestion to learn and optimize these hyperparameters is to use Vizier tool from TensorFlow and learn more optimal parameters that improves your model performance. So now that we have trained and updated our graph neural network, updated our graph with the GNN transformations, let's get a readout layer. So this was a graph level classification, right? So we need an encoding at the graph level. And the approach we have used here is pulling the node states at the context level using a mean aggregation of the node states. And this is going to be the readout feature. But remember, we also had this hidden state at the context that we declared earlier, which was the number of atoms and number of bonds in the molecule. So what we do is we want to also condition our model to make its decision based on both readout as well as this hidden state of the context. So we do a concatenation of these 2 features and then pass it through a linear transformation to acquire our logits and declare and return our model with the input being the input graph and output being the logits layer. So this was our function, and let's see how we are going to use this function to define the model and train it. So the function was using a bunch of different hyperparameters like the node dimension, edge dimension, next state, and etc. that you can drop out, alter regularization, etc. You can play with those parameters and see how it's going to affect the model performance. And now we get the Keras model, and also note that here we are using the element spec to get the graph tensor spec from the trained dataset, TF dataset. So you can look at the details of this graph tensor spec, which is used for the input layer in our functional API here. And our model is a binary classification for a binary classification task. So for the loss, we use this binary cross entropy because of that, and we also want to use binary accuracy as a matrix along with binary cross entropy. And to compile this model, we also need an optimizer, and we are using the Adam optimizer. And we are also declaring a learning rate decay. Using the cosine decay function, we can enable or disable that as well, which will basically help with reducing the learning rate throughout the training. So closer to the training getting complete, you will want to reduce your learning rate. It will start higher and get smaller throughout the training time. And we also use 200 epochs that you can also play with while training the model. So now that we compile with optimizer, loss, and metric values, you can call this model.summary method, which is going to show you the individual layers in your neural network, along with the number of parameters each has, and total number of trainable parameters that you have in your model. So now we can call model.fit to train this model. We pass this batch data sets from training and validation, and how many steps you need per epoch, and you can play with this epochs parameter as well and see how that's going to change the model performance. And you can see, the model.summary, model.fit returns a history data, which you can use to plot the loss and metric values, how they change throughout your training for both validation and train data sets. So you can see here an example for doing that. You can see for training how loss, binary accuracy, binary cross entropy changes. Similarly, validation, similarly those metrics, how they change for your validation data set throughout your training, where the x-axis is going to be apparently the epochs. Now let's take a look at a couple more advanced topics. So we mentioned this merge batch to components API, right? Which is the first API you need to call as soon as you get the graph tensor before continuing with your training, because TF-GNN library Keras layers work with scalar graphs. So let's see how does this work under the hood. So we first generate a data set using a batch size of 5. So we batch our data and get this graph tensor with its labels. You can tell this is not a scalar graph from its shape, and you can print out that graph tensor. And now we have 5 graphs in this unmerged graph tensor, right? So when we want to take a look at the node stats features, which is the hidden state feature we declared earlier, now we see a ragged tensor. It's a ragged tensor because we have variable number of atoms in each molecule in the graph. Each molecule, each batch graph, right? So each graph in the batch has a different number of nodes. So we can represent that through a ragged tensor. And similarly, if you look at these unmerged graph tensors bonds relation and its adjacency source tensor, it's also a ragged tensor representing, right, for each graph in the batch. You can see there is like 5 entries here. There is a variable number of edges per graph. So that's why we need to represent that as a ragged tensor. What will make it actually more easier to manage is now just merge these graphs. So now we have a scalar graph where each of these individual graphs is now a connected component of the merged scalar graph. So as soon as we call this scalar merge batch to components API, our shape is now for a scalar representation. You can see, there is 5 graphs in this graph tensor, but their node sets and edge sets are also merged. So basically now we use the same index vectors to represent the nodes and edges as if they belong to the same graph across these different subgraphs from the batch. And there is a way actually to find out the boundaries, because each individual graph is still connected within its own node set, not across the components. So our node sets, the atoms node sets now becomes a dense tensor. And you can see from the shape that there's 85 nodes in this batch graph, and you can play with the batch size, and you will see, this number will increase, because when we batch, we actually just treat as if it's just one graph, and the node set count is going to be the total nodes in this one merged scalar graph. And the second dimension is still the same fixed feature dimension we have for representing this one-hot encoding. And similarly, edge sets is also merged. Now we can see the total number of edges in this scalar graph is 180, and you can see the indexes are representing the full total number of edges in the scalar graph. Although they are not there is connected components which don't share any edges among them. There is let me show you also how you can find out the boundaries among these edge as well as node sets, right? So when you just index into these edge sets, graph piece, and look at the sizes tensor, we were disconnected. Oh, nice! It actually connected back. So the sizes tensors was keeping the number of entities, which can be node sets or edge sets, right, in the respective graph piece. Now, when we use or access that tensor, you can see that now there is 5 different pieces here, each showing the number of edges in each individual graph. In each individual graph. So the first graph has 28 edges, second 50, etc. And you can see the same thing from the node sets. Now let's take a look at a high-level example of the heterogeneous graph. So we have used here the OGB and MAC dataset. You can see the entity relation diagram for this heterogeneous graph. And we have a link to the full collab. You can go take a look at the example of how to build a TF-GNN model for this heterogeneous graph data. And here's an example that uses graph update. Now that we have multiple edge sets, our node sets dictionary consists of multiple entries for a node set update, and each node set has also different edge sets, and you can have a separate convolution for each of them, or even share parameters across them with an XState function. So now we are done with the teacher version of the collab, and in the student version, let me show you here. I don't know how much time we have left, but there is a question, a small task for you to modify the graph update. Here, to modify your graph update. So now at each graph transformation, at each graph update of your GNN layers, you can also learn an embedding, or sorry, learn an encoding for the context hidden state, and see how that will change the performance, and make changes in your readout layer accordingly.